So the question here is, in the circuit shown below, V1 and V2 are bias voltages full stop. Based on input and output impedances, the circuit behaves as a option A, voltage control voltage source, option B, voltage control current source, option C, current control voltage source, option D, current control current source. So this is the circuit given here, and in this circuit, let's say this is as a M1 and this is as a M2. So if you observe this circuit, under the AC analysis of this circuit, this V1, V2 and VDD, these all the DC sources will be short circuited, and by that way this M1 transistor is acting here as a active load. This is working here as an active load, and this M2 is working here as a driver transistor. So this is working as an amplifier whose active load is acted by this M1 transistor. Now here if you see that this AC signal is given to the source terminal of this M2 transistor, and their V2 will be at the ground, their gate will be at the ground as per their AC analysis. So this is working here, this M2 transistor is working here as a common gate configuration of this MOSFET or common gate amplifier of this MOSFET. This is very similar as like common base of the BJT. So the characteristic of common base will be followed here for this common gate amplifier. So this is working here as a common gate amplifier, and for the common gate amplifier, their input impedance or their input resistance will be low and their output resistance will be high. And as we know that this common base in BJT, it is working here as a current amplifier. In the similar fashion, this common gate amplifier also works here as a current amplifier. So current amplifier means their input is current, their output is current, and their gain will be defined output current by input current. So here we can say that their output current is controlled by their input current. So this is configured, or this is called here as a current control current source, and by that way that option D is the right answer for this question. And this is the question they had asked in GATE 2023 for EC as a MCQ of the question, and the final answer for this question is option D. By this way, this is the end of the explanation for this question. So the question here is, a cascade of common source amplifiers in a unity gain feedback configuration oscillates when option A, the closed loop gain is less than 1 and the phase shift is less than 180 degree. Option B, the closed loop gain is greater than 1 and the phase shift is less than 180 degree. Option C, the closed loop gain is less than 1 and the phase shift is greater than 180 degree. Option D, the closed loop gain is greater than 1 and the phase shift is greater than 180 degree. And this is the question they asked for the GATE 2023 for EC branch from the subject of analog. So here, as we know that for the oscillation, that as per the Barkhausen criteria to oscillate a circuit, their loop gain, it must be equal to 1 in the critical situation. And this loop gain is defined how? It is the product of A and beta, it should be equal to 1, where A is the gain of a normal amplifier and beta is the feedback gain of that feedback network. So here this A into beta, it must be equal to 1 as per their loop gain condition. And second condition is it should have their total phase shift. This should be 360 degree or multiple of 360 degree, where this n is equal to 1, 2, 3 and so on. So if these two conditions is satisfied by an oscillator circuit, then only it will oscillate. But here we have that critical condition, because if any of these two factor, either A or beta, if it is shrink to less than 1 or if their product is lesser than 1, then then it will not follow that oscillation. So due to that reason, it should not, their product should not fall below of this 1. We are keeping for the safer side to sustain the oscillation their loop gain as a into beta, their magnitude must be greater than equal to 1. So basically, to sustain the oscillation for the future, their product must be greater than equal to 1, and their phase shift also should be greater than 360 degree or equal to 360 degree. So here, as per the option, it has mentioned phase shift is greater than 180 degree. It means it is given 180 degree is for one stage, but here in the question it has mentioned cascade of multiple stages, cascade of common source amplifier. It means it is having more than one stages. So their overall phase shift should be greater than equal to 360 degree, and the magnitude of this A into beta should be greater than equal to 1. Then only it will sustain the oscillation as per the Barkhausen criteria. So as per this condition, that option D is satisfying for this question. So option D is the right answer for this question, and by this way, this is the end of the explanation for this question. So the question here is the V out by V in of the circuit shown below is, and this is the circuit shown here. So for this circuit, we need to find out the ratio of V out by V in, and their answer is given in all the 4 options. And this question they had asked in GATE 2023 for EC from the analog subject. So now if you'll see that how to find out this V out by V in, let's say there are 3 op amps, so we'll give the name here as a op amp 1, this is op amp 2, this is op amp 3. So if you see that this circuit analysis, then this op amp 1 is as per the input given here as a V in, this is working into inverting mode of the op amp, and similarly the common input is given to the non-inverting terminal of this op amp 2. So this is working as a non-inverting mode of this op amp. So this op amp 2 is working here as a non-inverting mode of this op amp, and the output of this first op amp and second op amp is given to the inverting terminal of this third op amp, and now we need to solve this accordingly. So for the first op amp, what will be the output? Let's say this is output to V1, and for the second op amp, let's say their output is V2. So first of all, we need to find out the output of V1 and V2 for these 2 op amp. So this can be written here as a V1 is equal to minus R2 by R1 into V in. So let's say this as a equation number 1 as a output of this first op amp. Now similarly for the second op amp, what will happen? So this V2 output will happen. This is working into non-inverting mode of this op amp, because this common input V in is provided here to the non-inverting terminal of this second op amp. So this V2 output, whatever this output will come here as a V2 output, will be 1 plus R2 by R1 into V in. Let's say this as a equation number 2. Now these two V1 and V2 is applying through this R1 and R3 to this op amp 3. So this is R3, this is R3 here. So let's say this node point, we can say it here as a P, and apply KCL at this node point P due to this V1, V2, and as per the virtual short, if the non-inverting terminal of this third op amp is at ground, it means this will be also at the ground. So this P point is having that ground. So now here if we will apply KCL at this P node point, then we will get it here V1 minus 0 divided by R3 plus V2 minus 0 divided by R3. So due to this V1 and V2, we are considering this as a incoming current. So I am taking this positive, and this sum of these two current is equal to the outgoing current which is passing through this R4. So here we can write this 0 minus V out divided by R4. So let's say this as a equation number 3, and from here what we'll get? We will get it here, V1 plus V2 is equal to minus of R3 divided by R4 into V out, and let's say this as a equation number 4. Now we need to substitute the values of V1 and V2, or whatever terms we got it for V1 and V2 from equation 1 and 2, and substitute into this equation 4. Then what we'll get? So we'll get it here, this minus R2 divided by R1 into V in as a V1, plus for V2 this will be 1 plus R2 by R1 into V in is equal to minus R3 by R4 into V out. So now if you solve this V in is common to both the terms, so this can be written minus R2 by R1 plus 1 plus R2 by R1 is equal to minus R3 by R4 into V out. So this term minus R2 by R1 plus R2 by R1 will be cancelling to each other. So we will get it here as a V in is equal to minus R3 by R4 into V out. But as per the question, we need to find out what? We need to find out the ratio of V out by V in. So for this we need to find out the terms. So this is giving here V out by V in is equal to minus R4 by R3. So we got this V out by V in as a minus R4 by R3, and if you will observe this circuit very carefully, then it is working here as instrumentation amplifier, and as per the answer we got it here, this is matching with option A. So option A is the right answer for this question, and by this way this is the end of the explanation for this question. So the question here is, in the circuit shown below, D1 and D2 are silicon diodes with cut-in voltage of 0.7 volt full stop. V in and V out are input and output voltages in volts full stop. The transfer characteristic is, so this is the circuit given here, and their corresponding transfer characteristic is given in all these four options. So we need to find out which one is the correct transfer characteristic for this given circuit. And this is the question they had asked for GATE 2023 for EC branch based on the topic of this diode circuit, and this is the question they ask as a MCQ. So now first of all, there are two diodes D1 and D2. We need to find out for which region of the input D1 diode conducts, and both are anti-parallel. So it indicates that for that particular region both the diode will not work at a time. So for which region of the input D1 diode will works, for which region of the input D2 diode will works, and for what region both the diode will not work. So we need to find out all these three reasons, and then accordingly as per their equation, as per their analysis, we can draw their input output characteristic. So here as per the question, it has given their cut-in voltage is 0.7 volt. It means this is having with the polarity of plus minus 0.7 volt. It will take the drop when D1 diode is in the conducting state, and here this is supported with the 1 volt of this DC source. So this is indicating here, as per the polarity minus plus minus plus, so their voltages will be added together, and this is giving here when V input is greater than 1.7 volt, then only D1 diode will start to conduct. Or we can write down here, this voltage will be how much? Whatever will have this V in and 0.7 will be subtracted from this V in because it is the drop across this D1 diode under the conducting state. So this V out will be how much? This V out is V in minus 0.7 volt. This equation is true only if V in is greater than equal to 1.7 volt. If the input is greater than equal to 1.7 volt, then only D1 diode will start to conduct, and this will produce the output voltage with this equation as a V out is equal to V in minus 0.7. It means if the input is lesser than 1.7, this D1 diode is not conducting. This D1 diode is not conducting. Now for this D2 diode, when it will conduct? So as per their polarity, they should have plus, this is minus, this is 0.7 volt. So now if you see that this DC voltage is having the polarity minus plus, and for this D2 diode it is plus minus. So this 0.7 will be subtracted from 1. So remaining is 0.3 volt. If the input voltage is lesser than 0.3 volt, then only D2 diode will start to conduct. It means if V input is greater than 0.3 volt and lesser than 1.7 volt, then in this case D1 and D2 both will not conduct. And by that time, what will be the output voltage? If this is open circuit, it means here at this V out we will have open circuited voltage as a DC voltage of this 1 volt. So this V out will have, in this situation, this V out will have as a 1 volt. Now if this input is lesser than 0.3 volt, if V in is lesser than 0.3 volt, then D2 will conduct. And how will get this voltage? As per the polarity, here it is like if it is lesser than 0.3, so some part will be positive as a 0 to 0.3, and then the rest of the part will be negative. So how we can calculate this voltage? As per their voltage polarity, whenever it is having here as a plus minus, then it should be minus plus, and minus plus both will be added together, and then we will get it this V out. Whenever it is changing their polarity as a here minus, here plus, then their second node is minus, and that voltage whatever it is appearing here, and then plus 0.7, so that will become their output voltage for the negative. It means from 0 negative onwards. So this equation is best described by the graph which is plotted in between V out and V in, which is shown in option A. So option A is the right answer for this question, and by this way this is the end of the explanation for this question. So the question here is, the H parameters of a two-port network are shown below, full stop. The condition for the maximum small signal voltage gain as V out by Vs is, and this is the circuit given here, and their option is option A, H11 is equal to 0, H12 is equal to 0, H21 is equal to very high, and H22 is equal to 0. Option B, H11 is equal to very high, H12 is equal to 0, H21 is equal to very high, and H22 is equal to 0. Option C, H11 is equal to 0, H12 is equal to very high, H21 is equal to very high, and H22 is equal to 0. Option D, H11 is equal to 0, H12 is equal to 0, H21 is equal to very high, and H22 is equal to very high. So this is the question they had asked in GATE 2023 for EC from the analog topic, and this is the question basically based on that hybrid parameter of the transistor or H parameter of the transistor. So here we need to find out the condition for which their V out by Vs is maximum. So for this thing we need to solve this circuit as the input part as well as their output part, and then we need to find out the ratio of V out by Vs, which is called the gain of this circuit, and then accordingly we can find out their condition. So now first of all we'll apply that this KVL in this input side of the loop, and here we can write this as a V1 is equal to this V1 is equal to, here is the V1, so this voltage V1 is equal to the voltage across this, across H11, so the voltage across this H11 will become as a I1. H11 I1 is the voltage across this H11, and the voltage across this it has given as a H12 into V2. Let's say this as a equation number 1. Similarly, now we can apply KCL at this point, at this node in the output part of the circuit, and here we can write this as a I2 is the incoming current at this node point, and one current is going through this as a H21 into V1, and another part of the current is going through this H22. So here we can write this current as a I2. So this I2 is equal to, this I2 is equal to H21 V1 plus H22 into V2. Let's say this as a equation number 2. Now we need to find out this V out. So V out will be what? This V out we can write here. So output voltage will be the voltage across this RL, and this I2 is passing through this RL. So their polarity, if I2 is passing from this side, so this will be plus here and this will be minus. So we can write down here with reference to V out, their polarity across the RL is opposite. So we can write this V2 or V out is equal to minus I2 into RL. Minus I2 into RL. Let's say this as a equation number 3. Now substitute the value of this I2 from this equation 2 into this equation 3. We will get it here. V out is equal to minus H21 V1 plus H22 V2 into RL. So here we can rewrite this as a minus H21 V1 into RL minus this V2 is what? This V2 is the same, this node point is called V2, and that is similar to this V out. So here we can write this as a H22 V2 into RL. So here we can write H21 V1 RL, and at the place of V2 we can substitute this as a V out. So here this will become H22 V out into RL. Now take this term left side so that it will become V out, will take it common, so we can write it here 1 plus H22 into RL is equal to minus H21 V1 into RL. So here now we can write this V out divide by V1 is equal to Vs. So directly we can write V out by Vs is equal to minus H21 into RL divide by 1 plus H22 RL. So if you'll see that in this expression here, whatever we have this V1, this V1 is nothing but this is Vs here, because if you'll see that in this circuit part, so here it is showing that this is the polarity for this V1 as like this is plus, this is minus, and this V1 is very parallel to this Vs, so we can substitute V1 as a Vs, and from this output side we can substitute V out as a V2. So by using this notation, we will get it here as a V out by Vs is equal to minus H21 RL divided by 1 plus H22 RL. So to make it here maximum, for example, in the ideal case, what should be there? If Vs is 0, if Vs is 0, it means this is giving the indication that V output by 0. So this ratio will be approaching to infinite in the ideal case. So to make it Vs 0, it means Vs is equal to V1 is equal to, what is there? So if you will see that this V1 is equal to H11 I1 plus H12 V2. H11 I1 plus H12 V2. So here to make it 0, this to make it Vs as a 0, what should be the condition? That this I1 cannot be 0, V2 cannot be 0. So what parameter should be 0? This H11 it should be 0, H12 it should be 0. So here we can say that to get this maximum H11 value it should be 0 and H12 should be 0. Now from this expression, whatever we got it here, from here to get it this gain as a highest, the magnitude of this, like we are talking about that magnitude, so we should not take the consideration of this minus sign here. So to make it maximum, this H21 should be maximum or it should be very high. Then in that case also their gain will be very high. At the same time, denominator, if it is lesser, then also their gain will be higher. So RL cannot be 0. So what can be 0? This H22 can be 0. So here we can say that this H22 should be 0. So we got here H11 is equal to 0, H12 is equal to 0, H22 is equal to 0 and H21 should be high. So now we'll check it with the option. So if you'll see that in the option, here in option A, H11 is equal to 0, H12 is equal to 0, H21 is equal to very high and H22 is equal to 0. So as per the derivation what we got it there, to make it V out by Vs as a maximum, we got this and this is matching with option A. So option A is the right answer for this question, and by this way this is the end of the explanation for this question. So the question here is, in the circuit below, the voltage VL is fill in the blanks volt and answer should be round off to 2 decimal places full stop. And this is the question they ask in GATE 2023 for EC as a NAT type of the question, and this question belongs to EDC of the subject based on the topic of MOSFET, and the main concept used here is current mirror circuit. So let's say in this circuit I can give the name here for this MOSFET as a M1, for this MOSFET as a M2, for this MOSFET as a M3, for this MOSFET as a M4, for this MOSFET as a M5. So there are 5 MOSFET used in this one, and here as we know that for this MOSFET, this is the MOSFET where this is the source terminal, this is their gate terminal, and this is their drain terminal. So as we know that when drain is shorted to the gate, then it indicates that particular MOSFET must have to work into saturation region. And as we know that the expression for the saturation region is ID sat is equal to 1 by 2 mu P. This is the P type of the channel here, or this is the P type of the semiconductor here. So 1 by 2 mu P into COX W by L into magnitude of VGS minus magnitude of this VT and their whole square. So this indicates that if the transistors are similar, it means their 1 by 2 mu P COX value will be same, and VGS is common here for this M1 transistor as well as for this M2 transistor. and Vt is also same as per both the transistors are identical, only these two transistors are different with respect to W by L ratio. So here for the M1 transistor W by L is 1, and for M2 transistor W by L ratio is 10. So due to that reason, the current carrying capability for this M2 transistor will be different. So let's say for this part, for the M1 transistor, this is basically current mirror circuit here, and in this current mirror circuit, this M1 transistor will be working here as a driver transistor, and rest of the part it is acting for this M1 transistor as a load transistor. Similarly, for this M4 and M5, this M4 works as a driver transistor for this part of the current mirror circuit, and this M5 is working as a load transistor for this part of the M4 as a driver circuit. So now here, first we'll analyze for this M1, M2, M3. So if there 1 by 2 mu p cox, this is the constant term for all the transistors for the p type, and this VGS is common for M1, M2, M3. Their Vt is same. So here their current carrying capability will depends upon the ratio of W by L. So due to that reason, how it will be affecting? So this is giving here the idea that for this M1 transistor, their IM1, I can say that their current is IM1 is given here as a 1 milliampere. So as a ratio for this and this transistor, like for the M1 and M2, how it will be changing? So I can say that this IM1 for this M1 transistor divided by IM2 for this M2 transistor, IM2, if all the parameters are same here, it means it will depending upon their W by L ratio. So W by L ratio for the M1 transistor divided by W by L ratio for M2 transistor. So from this one we will get it here IM2 as a W by L 2 divided by W by L for the first transistor into IM1. So here this W by L ratio for this M2 transistor is given as a 10 divided by W by L ratio for this M1 transistor is 1. So this is 1, and IM1 it has given as a 1 milliampere. So this is 1 milliampere. So we got it here as a IM2 is 10 milliampere. This is 10 milliampere. Similarly with the same concept, we will take the ratio of IM1 by IM3 for this M3 of the transistor, and there we'll get it here this IM3 as a, how? This will be 7 milliampere. Now through this IM2, whatever is the current coming from source, it is passing through their drain terminal, because as we know that gate current for any type of the transistor as a MOSFET, either it is P channel or M channel, their gate current is almost equal to 0. It means this IM2 is flowing, whatever it is flowing from the source, the same current will flow through their drain of this M2 transistor, and the same current is passing through this M4 also. So for M4, what will happen? This IM4 current will be, this IM4 will become here as a, how much? It will be 10 milliampere. 10 milliampere. Now we'll correlate this M4 and M5. So here we can write it here. This IM4, whatever we got it here as a 10 milliampere, and with the same concept whatever I had explained earlier, we'll get this IM5 as a WL for the fifth transistor divided by W by L for the fourth transistor into IM4 with the same concept as like IM4 divided by IM5 is equal to W by L of the fourth transistor divided by W by L of the fifth transistor. So with the same concept we got it here. This W by L for the fifth transistor, it is having 5. It has given in the figure itself. And W by L for the fourth transistor, it is 10 here. And IM4 we got it here as a 10 milliampere. So we'll get it here as a 5 milliampere. So we'll come to the figure again. So here this IM5 it is showing, this IM5 we got it here as a 5 milliampere. This we got it here as a 5 milliampere. At this node point, whatever current is coming as a IM3, this is here 7 milliampere. The same current, whatever it is 7 milliampere, it is coming to this node point. Out of 7, 5 milliampere is going as a IM5 through the drain to source of this M5 transistor. It means remaining 2 milliampere is flowing through this 1 kilo ohm of the resistor. So through this it is passing here as a 2 milliampere, so that their VL voltage will be how much? Their VL voltage VL is equal to 1 kilo ohm. The voltage appeared across this resistor. How much it will be? 1 kilo ohm into 2 milliampere. Into 2 milliampere. So kilo milli gets cancelled and we'll get here as a 2 volt. We'll get it here as a 2 volt. So the VL voltage for this question we got it here as a 2 volt. So the numerical values for this question, their answer is 2 here, and that is the final answer. By this way, this is the end of the explanation for this question.